So I got Thomas. No, you're not Thomas. What's your name? Andrew. I'm sorry. So this is my homie Andrew, and you're asking about
velocity, position, and
just the graphs in general. Okay. So in physics, we deal with position time, velocity time, acceleration time graphs. Position is x, velocity v, acceleration a. These are quite common. And how do you want the object to be moving?
just speeding up.
Speeding up? Speeding up or slowing down or both?
Both.
Both? Oh god, okay. So I'll do it like the mousetrap car. Speeds up would be that. And then let's say it stops speeding up and it starts slowing down, so the concavity changes, right?
Yeah.
Something like that. How's that looking? And I'll draw a dotted vertical line there so that my graphs correspond with one another. Does that sound good?
Yeah.
All right. So for my velocity graph, I'm having my object move in the positive direction. So let's say the object started from rest and sped up in the positive direction. And then in the second segment of time, it's actually going to slow down, right, to a stop. I'm just reading the slopes of my position graph to figure that out. And then if I go to my acceleration graph, I have a positive slope, positive acceleration, and I'm just going to make this simple and say that my acceleration at the end is negative and the same magnitude, right? So in general, we can say that the slope, whoops, that was weird. All right, I'll just put an S there. Slope of our position versus time graph is what? Is slope of our position time graph is our velocity. Good. And when you have a curved graph, you have to take the slopes of the tangent lines, right? All right. Now, the slope of our velocity versus time, right? V versus t graph is what? Good. Now, one of the things we talked about a little bit in class today was the meaning of, well, you already know that this area here and this area here, it looks like our object, does our object return back to the position where it started? No. The position, you read from the position graph, it started at 0 and ended up some later positive position. But on our velocity graph, don't get fooled, that velocity graph shows how you're moving. And what happened is it started at the same velocity that it ended with. Meaning, in the beginning it was at rest, and in the end it was at rest, because in the beginning and end the velocity was 0. Okay? So this area here is our change in position, otherwise known as displacement, right? And it looks like our total displacement is some positive number. Whatever this value is here is our displacement, right? And then we have the area of our acceleration graphs, which is what? What's the area of an acceleration graph? Well, you can use the units to figure it out. Both of these areas are just rectangles, right? And the acceleration, let's just say it's measured in meters per second squared. Well, you're multiplying meters per second squared times seconds. What do you get?
Meters cubed.
No, meters per second squared times seconds. So if you got meters per second squared times seconds, when you calculate those areas, you'll be left with what?
Meters per second.
Just meters per second, yeah. And that is a measurement of what? Well, it could be speed, but areas of graphs are always changes in something.
Just change in speed.
You're getting closer, dude. It's a change, not speed, but
Velocity.
it's a change in velocity. So these graphs are really intimately connected. The slope of a position time graph is our velocity. The slope of a velocity graph is our acceleration. The area of our acceleration time graph is our
Velocity. Or change of velocity.
change in velocity. Good. And the area of our velocity graph is a change in
Just place.
which is a change in.
Position.
Good. Yeah. So I can see you're getting comfortable with the vocabulary. That's why we stack our graphs vertically in physics. We like to stack our graphs because then the logic behind how these things are connected reveals itself better. So as you go down, think of the slope of the position graph being our velocity and the slope of our velocity graph being our acceleration. As you go up, think of the areas and how they're related. The area of your acceleration graph is a change in velocity, and the area of our velocity graph is a change in position. Anyway, hope that helps. That's 6 minutes. And I'll put this up on the website for everybody to enjoy.